as the point. Lastly, I take x as minus 2. So minus mod x is minus of mod of minus 2, which is minus 2. And I get minus 2 comma minus 2. When I join these points, this is the graph of minus mod x that I get. So now at this point of time, you have both the graphs of mod x as well as minus mod x with you together in the same Cartesian plane. What do you observe? See, if I take x-axis as the mirror, just treat x-axis as the mirror for a while. Do you agree that minus mod x is nothing but the mirror image of mod x only? Yes, isn't it? That means if you take the graph of mod x and you vertically flip it about the x-axis, you get the graph of minus mod x. Yes, that's it. This is the answer to your question. This is not just valid for mod x, this is valid actually for any function f. It is that if you have the graph of f with you and you vertically flip it about the x-axis, you end up getting the graph of minus f with you. That's it, end of the story. Okay, this is something that you have to keep in mind throughout today's lecture. Right? Now let's begin tracing the graphs of the 6 beautiful trigonometric functions: sine, cos, tan, cosec, sec, and cot. The first task is to sketch the graph of the sine function. For that, let's quickly recall the unit circle. We have learned that the y coordinate of any point P sitting on the unit circle is nothing but equal to sine theta, where theta is the angle corresponding to P. That means theta is the angle which OP makes with the positive direction of x-axis in the anti-clockwise sense. We are interested to know how does sine theta change for varying values of theta. So for that, let us plot the values of theta along the x-axis and the corresponding values of sine theta along the y-axis. See, when theta is 0, that means P is sitting here at 1, 0, then sine theta is equal to the y coordinate of P, which is 0, which gives you sine 0 is 0. Further, when theta starts increasing from 0 in the first quadrant, see what's happening? Simultaneously, the y coordinate of point P is positive and starts increasing. Yes, that means when theta increases from 0 in the first quadrant, sine theta is positive and is increasing. When theta reaches pi by 2, in that case, P reaches the point 0, 1. That means sine theta is equal to y coordinate of P, which is 1. So this gives you sine 90 is 1. Further, when theta increases from pi by 2 in the second quadrant, what do you see? Simultaneously, the y coordinate of point P is positive but is decreasing. That means when theta increases from pi by 2 in the second quadrant, sine theta is positive but starts decreasing. Yes. Now, when theta reaches pi, that means P reaches minus 1, 0, then sine theta is the y coordinate of P, which is 0, which gives you sine pi is 0. Yes. So what do you observe? What do you observe? You have simply observed that at theta equals 0, sine theta is 0. At theta equals pi by 2, sine theta is 1. And also, when theta is equal to pi, sine theta is again 0. Moreover, when theta is strictly sandwiched between 0 and pi, sine theta is strictly positive. Yes. Let's move ahead. Now I am saying theta is increasing from pi in the third quadrant, then you can observe that correspondingly, the y coordinate of point P becomes negative and starts decreasing. That means what? What does this give you? This simply gives you that when theta increases from pi in the third quadrant, sine theta becomes negative and is decreasing. And once theta reaches 3 pi by 2, that means P reaches 0, -1, then sine theta is equal to y coordinate of p, which is -1, and this gives you sine 3 pi by 2 is -1. Further, when theta increases from 3 pi by 2 in the fourth quadrant, what is happening? Just take a look at it. Did you observe what happened? When theta increases from 3 pi by 2 in the fourth quadrant, the y coordinate of p is still negative but starts increasing. That means when theta increases from 3 pi by 2 in the fourth quadrant, sine theta remains negative but is increasing. And when one revolution is completed, that means when theta reaches 2 pi or p reaches again the point 1 comma 0, then sine theta is equal to y coordinate of p, which is 0. That gives you sine 2 pi is 0. So what have you observed? Tell me. We have observed that sine pi is 0. Further, sine 3 pi by 2 is equal to -1. And further, when theta is equal to 2 pi, then sine theta is equal to again 0. Also, when theta is strictly sandwiched between pi and 2 pi, sine theta is strictly negative. And this gives you the graph of the sine function in the interval 0 to 2 pi. Okay then, now that I have the graph of the sine function in the interval 0 to 2 pi, I am extremely curious to find out how does sine function behave for angles greater than 2 pi and less than 0. Let's find out. So right now I have with me the graph of the sine function in the interval 0 to 2 pi, which is one interval of length 2 pi. First of all, I am going to plot the graph of the sine function in the immediate next interval of length 2 pi, which is 2 pi to 4 pi. Got it? I'm sure you would agree with me when I say that if theta is an angle lying in 0 to 2 pi, then 2 pi plus theta will be an angle lying in 2 pi to 4 pi. Isn't it? If theta is sandwiched between 0 and 2 pi, if I add 2 pi throughout this inequality, I get 2 pi plus theta sandwiched between 2 pi and 4 pi. And we know as a matter of fact that sine of 2 pi plus theta is exactly same as sine theta. So what are you getting? You are getting that corresponding to all the angles theta in the interval 0 to 2 pi, you respectively have angles 2 pi plus theta in the interval 2 pi to 4 pi, such that sine of 2 pi plus theta is exactly same as sine theta. That means whatever is the behavior of the sine function in the interval 0 to 2 pi, exact same photocopy will be the behavior of the sine function in 2 pi to 4 pi. That is why the graph of the sine function in the interval 0 to 2 pi and 2 pi to 4 pi is exactly the same, as you can see. Now that I have the graph of the sine function in 0 to 2 pi as well as 2 pi to 4 pi, that means completely 0 to 4 pi, next target will be to find the graph of the sine function in the further next interval of length 2 pi, which is 4 pi to 6 pi, using the exact same strategy. See, if I take theta to be an angle lying in 2 pi to 4 pi, then obviously 2 pi plus theta will be an angle lying in 4 pi to 6 pi. And again, sine of 2 pi plus theta is same as sine theta. That means what are you getting? You are getting that corresponding to each and every angle theta in 2 pi to 4 pi, I have a respective angle 2 pi plus theta in the interval 4 pi to 6 pi, such that sine of 2 pi plus theta is same as sine theta. That means again, whatever is the graph of the sine in 2 pi to 4 pi, replica of it will be the graph of sine in the interval 4 pi to 6 pi. Similarly, replica of this will be the graph of the sine in 6 pi to 8 pi, 8 pi to 10 pi, 10 pi to 12 pi, and so on. That's how you get the graph of the sine function corresponding to the non-negative x-axis. Coming to the negative x-axis, I'm going to adopt the exact same drill, okay? In here, this is the interval of length 2 pi in which I'm interested to plot the graph of the sine function. So, let me take theta to be an angle belonging in 0 to 2 pi. Then obviously, minus 2 pi plus theta will belong in minus 2 pi to 0. Convinced? See, if theta is lying in 0 to 2 pi, then minus 2 pi plus theta will be lying in minus 2 pi to 0. I just added minus 2 pi throughout. Yes, and I again know that sine of minus 2 pi plus theta is also same as sine theta. So what are you getting? That corresponding to each and every angle theta in 0 to 2 pi, I have a respective angle minus 2 pi plus theta in the interval minus 2 pi to 0, such that sine of minus 2 pi plus theta is same as sine theta. That means whatever is the behavior of the sine function in 0 to 2 pi, exact same will be the behavior of the sine in the interval minus 2 pi to 0 as well. So whatever is the graph in 0 to 2 pi, its photocopy is the graph in minus 2 pi to 0. Got it? Now, further next, exact same strategy. Now I'm interested to obtain the graph of the sine function in the further next interval of length 2 pi, which is minus 4 pi to minus 2 pi. So what I'm going to do, if theta is an angle lying in the interval minus 2 pi to 0, obviously minus 2 pi plus theta will be an angle lying in minus 4 pi to minus 2 pi. Yes, and again sine of minus 2 pi plus theta is same as sine theta. So what are you getting? That corresponding to each and every angle theta in this interval minus 2 pi to 0, I have a respective angle minus 2 pi plus theta in the interval minus 4 pi to minus 2 pi. And because sine of minus 2 pi plus theta is same as sine theta, that's why the graph of the sine function in minus 4 pi to minus 2 pi will be exactly same as the graph of the sine function in minus 2 pi to 0. Further, in minus 6 pi to minus 4 pi, we'll get the same graph. Minus 8 pi to minus 6 pi, we'll get the same graph, and so on. That means you've also now obtained the graph of the sine function corresponding to the negative x-axis, and hence you are done with getting your entire graph corresponding to the complete real line. Do you get it? This gives you what? The very first and crucial observation. You can see that the sine graph is drawn corresponding to the entire x-axis. That means sine theta is defined for every real theta. So I can say that the domain of the sine function is definitely set of all reals. Yes, but observe one more thing. If you just focus on the graph of sine in the interval 0 to 2 pi, then you will find out that the exact same ditto graph is existing in the interval 2 pi to 4 pi, in the interval 4 pi to 6 pi, in the interval 6 pi to 8 pi, 8 pi to 10 pi, and so on, in the interval minus 2 pi to 0, in the interval minus 4 pi to minus 2 pi, and so on. Such functions are called periodic. In here, sine function is periodic. Why? Because it is reoccurring or repeating itself at regular intervals. In fact, to be precise, sine is a periodic function with period 2 pi. Why? Because if I take this interval of length 2 pi, whatever is the behavior of sine in this interval of length 2 pi, exact same is the behavior of sine function in the consecutive intervals of length 2 pi to the right of this interval as well as to the left of this interval. Got it? And that's why whenever you want to extract out any information about the sine function, it is enough to just draw the graph of the sine function in one interval of length 2 pi. You don't need the graph of sine over the complete real line. Just any one interval of length 2 pi is enough. Why? Because it is going to repeat its behavior in all the consecutive intervals of length 2 pi. Got it? Right? A very, very interesting observation about the sine function. It is periodic with period 2 pi. Further observe that if I draw two lines, y equals 1 and y equals minus 1, what can you see? The entire graph is sandwiched between these two lines. Yes, that means theta is coming from the complete x-axis, but sine theta is only taking values from minus 1 to 1. Do you agree? Corresponding to any real theta, sine theta is always between minus 1 and 1. It is oscillating between minus 1 and 1. So what do you see? That as the graph is moving from bottom to top again and again and again, it is only sweeping values from minus 1 to 1, and hence I say that the range of the sine function is minus 1 comma 1 closed interval. Or I can say that sine theta is sandwiched between minus 1 and 1 for every real value of theta. This means there is absolutely no real theta for which sine theta is greater than 1, and there is absolutely no value of theta for which sine theta is less than minus 1. So the maximum value of sine theta for any theta is 1, and the minimum value of sine theta is minus 1. Got it? Understood? And hence we have some amazing observations about the sine function that, as justified, its domain is set of all reals. Its range is minus 1 comma 1 closed interval. That means its minimum value is minus 1. Maximum value is 1. So sine cannot exceed 1 and sine can never be less than minus 1. Remember this. Further, if you look at the graph carefully, where all is the graph intersecting the x-axis? Take a look. It is intersecting the x-axis at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, and so on, minus pi, minus 2 pi, minus 3 pi, minus 4 pi, minus 5 pi, and so on. That means the graph is only intersecting the x-axis at all the integral multiples of pi. So it's justified that at every integral multiple of pi, sine is 0, or when theta is any integral multiple of pi, sine is 0. In fact, sine is 0 only when theta is an integral multiple of pi. That's it. Okay, fine. And further, this is something that we already know, that sine pulls out the minus sign. Sine of minus theta is minus sine theta. Yes, for every real theta. And again, a reinforcement, we have to remember this, that sine is a periodic function with period 2 pi. Okay, let's now move on and trace the graph of the cosine function. Now, before we jump on to plotting the graph of the cosine function, realize that you are already aware of the cosine ratios of 5 basic angles: 0, 30, 45, 60, and 90. So let's use this fact and plot the graph of the cosine function in the interval 0 to 90, that is 0 to pi by 2. Okay, so I know cos 0 is 1, cos 30 is root 3 by 2, cos 45 is 1 by root 2, cos 60 is 1 by 2, and cos 90 is 0. Hence, this is the graph of the cosine function that I get in the interval 0 to pi by 2. Similarly, let's take few angles between pi by 2 and pi and plot the graph of cos function in the interval pi by 2 to pi. Let's begin. If I take theta as 2 pi by 3, what is cos 2 pi by 3? Well, 2 pi by 3 is certainly 120 degrees, which is definitely lying between pi by 2 and pi. First of all, you should be justified of that. Now, when I talk about cos of 2 pi by 3, it is same as pi minus pi by 3. This will be equal to what? We have learned trigonometric ratios of allied angles. In here there is pi, so this will become cos of pi by 3, also pi minus pi by 3. That means pi minus pi by 3 lies in the second quadrant. In the second quadrant, cos is negative, so you get minus cos 60, which is minus 1 by 2. Got it? Similarly, let's take another angle as 3 pi by 4. This is same as cos of pi minus pi by 4, which will be equal to minus cos pi by 4, that is minus 1 by root 2. Similarly, next angle I take as 5 pi by 6, which is same as pi minus pi by 6. Yes, and cos of pi minus pi by 6 is equal to minus cos pi by 6. That means minus cos 30, which is minus root 3 by 2. Lastly, I take theta as pi. So cos pi comes out to be what? We have learned about it. It is equal to minus 1. Yes. Now, when I join these points, I get this to be the graph of the cos function in the interval pi by 2 to pi, and hence I end up getting this to be the graph of the cos function in the interval 0 to pi. Now, I want to get the graph of cos function corresponding to angles greater than pi as well. So, realize one thing, that if theta lies here, that means when theta is sandwiched between 0 and pi plus theta is sandwiched between pi and 2 pi. That means pi plus theta lies here. And we know cos of pi plus theta is equal to minus cos theta. Do you agree? Because there's pi, cos of pi plus theta, magnitude will be equal to cos theta only. And pi plus theta lies where? In the third quadrant. In the third quadrant, cos is negative. So you get cos of pi plus theta equal to minus cos theta. That means what? Whatever is the graph of cos in the interval 0 to pi, its negative will be the graph of cos in the interval pi to 2 pi. So what to do? Just flip this pink graph that you can see vertically about the x-axis and bingo, you get the graph of the cos function in the interval pi to 2 pi. and hence I have the graph of the cosine function in the complete interval 0 to 2 pi, but I still am curious to know the behavior of the cosine function for angles greater than 2 pi as well as less than 0. So let's see. See, if theta lies here, that means if theta is sandwiched between 0 and 2 pi, obviously minus theta will be sandwiched between minus 2 pi and 0. That means minus theta will lie here in this interval. And I know cos of minus theta is same as cos theta because cos gulps in the minus sign. Yeah, that means what? Whatever is the graph of the cos function in the interval 0 to 2 pi, exact same will be the graph of the cos function in the interval minus 2 pi to 0. Now I have the graph of the cosine function in the interval minus 2 pi to 2 pi. Okay, let me take this as theta. That means theta is coming from 0 to 2 pi interval. Then 2 pi plus theta will come from 2 pi to 4 pi interval. And I know cos of 2 pi plus theta is same as cos theta. That means whatever is the graph of cos in the interval 0 to 2 pi, exact same is the graph of cos in the interval 2 pi to 4 pi, exact same is the graph of cos in the interval 4 pi to 6 pi, exact same is the graph of cos in the interval 6 pi to 8 pi, 8 pi to 10 pi, and so on. Coming to the negative x-axis, if I take this theta, that means theta is the angle between minus 2 pi and 0, then minus 2 pi plus theta will lie in this interval, minus 4 pi to minus 2 pi. And cos of minus 2 pi plus theta is same as cos theta. So whatever is the graph of cos in the interval minus 2 pi to 0, replica is the graph of cos in the interval minus 4 pi to minus 2 pi. Exact same is the graph of cos in the interval minus 6 pi to minus 4 pi, minus 8 pi to minus 6 pi, and so on. And hence, you end up getting this to be the graph of the cosine function corresponding to the entire real line. So again, because the graph of cos is drawn corresponding to the complete x-axis, that means cos theta is defined for every real theta. So this means what? The domain of this particular function is again set of all reals. That's one observation. Yeah. Moreover, if you just focus on the graph of cos in the interval 0 to 2 pi, just focus on this portion of the graph, then you will observe that the exact same graph is repeated in the interval 2 pi to 4 pi, 4 pi to 6 pi, 6 pi to 8 pi, and so on, minus 2 pi to 0, minus 4 pi to minus 2 pi, minus 6 pi to minus 4 pi, and so on. That means even cos is a periodic function because it is repeating its behavior or it is reoccurring at regular intervals. In fact, to be very precise, cos is a periodic function with period 2 pi. Why? Because whatever is the behavior of the cos function in this interval of length 2 pi, exact same ditto photocopy is the behavior of the cos function in every consecutive interval of length 2 pi to the right of this interval or to the left of this interval. Do you agree? And hence we know that cos is a periodic function with period 2 pi. So whenever you want to extract out any information about the cos function, it is sufficient for you to just plot its graph in any one interval of length 2 pi and extract out whatever information you want, because exact same replica graph will be drawn in all the consecutive intervals of length 2 pi. Fine. Next thing, observe that again, this complete graph is sandwiched between two lines, y equals 1 and y equals minus 1. That means same thing. Same thing, when theta varies over the complete real line, sine theta only varies from minus 1 to 1. So the range of this function is closed interval minus 1 to 1. Yes, as the graph is moving from bottom to top, it is actually just oscillating between minus 1 and 1, and hence it is sweeping all real numbers from minus 1 to 1 along the y-axis. That's why this interval is the range. Moreover, I can say there is absolutely no real theta for which cos theta is greater than 1, and there is absolutely no real theta for which cos theta is less than minus 1, because 1 is the max of cos, minus 1 is the min of cos. Got it? Another thing to observe is where all is this graph intersecting the x-axis. Just take a look at it. Pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2, 9 pi by 2, 11 pi by 2, and so on, minus pi by 2, minus 3 pi by 2, minus 5 pi by 2, minus 7 pi by 2, and so on. That means the graph of the cosine function is intersecting the x-axis at all the odd integral multiples of pi by 2. That means when theta is any odd integral multiple of pi by 2, cos of that theta is 0. In fact, cos of an angle is 0 only and only when that angle is an odd integral multiple of pi by 2. If it's not an odd integral multiple of pi by 2, cos of that angle is not 0. Got it? And hence, let's check out the observations about the cos function. Domain is set of all reals. Range is -1, 1 closed interval. So the min value of cos is -1 and the max is 1. As justified, cos is 0 only when the angle is an odd integral multiple of pi by 2. We already know cos of minus theta is cos theta. Cos gulps in the minus sign. And the period of cos function is 2 pi. Yes, let's now move ahead and check out the next trigonometric functions graph. Next up, we have the tan function. But before I jump on to plotting its graph straight away, let's quickly recollect everything we know about tan till now. See, tan is nothing but sine upon cos. Anything upon 0 we know is not defined. That means sine upon cos will exist as a real quantity only when cos is non-zero. The denominator is non-zero, right? That means tan will exist as a real quantity if and only if cos is non-zero. Now we know that cos of an angle is 0 only when that angle is an odd integral multiple of pi by 2. Right? So tan will exist as a real quantity only for those angles which are not an odd integral multiple of pi by 2. Or in other words, I can say tan of an angle doesn't exist as a real quantity when that angle is an odd integral multiple of pi by 2. So this gives you a very beautiful conclusion that tan of every angle exists except all the odd integral multiples of pi by 2. Okay, that means domain of the tan function is all reals except all the odd integral multiples of pi by 2. Yes, tan is not defined for any odd integral multiple of pi by 2, and that's why in the graph of tan, you see these dotted lines corresponding to all the odd integral multiples of pi by 2. Got it? Because there is no tan value existing corresponding to these angles. Right? So keeping this in mind, let's begin plotting the graph of tan. I already know the tan ratio of 5 basic angles, 0, 30, 45, 60, 90. So let's recollect them. I know tan 0 is 0. Okay. Tan 30 is 1 by root 3. Tan 45 is 1. Tan 60 is root 3. And obviously tan 90, as I just justified to you, doesn't exist. So when you join these points, this is the graph of the tan function you get corresponding to 0 to pi by 2 interval, where 0 is closed, pi by 2 is open. Now what can you see? See, this graph is never ever going to touch this dotted line x equals pi by 2. Never. It will keep on getting closer and closer to this dotted line, but it will never touch or intersect this dotted line. Because if it touches or intersects this dotted line, it would mean that tan of pi by 2 is existing as a real quantity, which is absolutely rubbish. Right? That is how this happens to be the graph of the tan function in the interval 0 to pi by 2, closed at 0, open at pi by 2. This is the graph of the tan function in the interval minus pi by 2 to 0. Okay. Once you have the graph of tan in the interval minus pi by 2 to pi by 2, obviously open interval, I want the graph of tan corresponding to angles greater than pi by 2 as well as less than minus pi by 2. So let's see, how can we get that? If I take theta here, that means if theta is lying between minus pi by 2 and pi by 2, then obviously pi plus theta will lie between pi by 2 and 3 pi by 2. And what is tan of pi plus theta? What is tan of pi plus theta? Do you remember? It is equal to tan theta. How? Because of pi, magnitude is tan theta, and pi plus theta lies in the third quadrant. In the third quadrant, tan is positive. Hence, you get plus tan theta, that is tan theta. So, what is the conclusion? Whatever is the graph of tan in the interval minus pi by 2 to pi by 2, exact same replica is the graph of tan in the interval pi by 2 to 3 pi by 2. Exactly same will be the graph of tan in the next interval 3 pi by 2 to 5 pi by 2, further next 5 pi by 2 to 7 pi by 2, and so on. Right? Now, let's get the graph of tan in the interval minus 3 pi by 2 to minus pi by 2. How? Well, I'm going to take theta here. So theta is sandwiched between minus pi by 2 and pi by 2, strictly, obviously. Yes. Then, what about minus pi plus theta? Well, it will be sandwiched between minus 3 pi by 2 and minus pi by 2. And what is tan of minus pi plus theta? Can you tell me? Can you tell me what is tan of minus pi plus theta? Let's resolve this. I can write this as tan of pi minus theta. Then this minus sign will come outside. This becomes minus tan of pi minus theta. Let's resolve tan of pi minus theta. This is tan theta, and pi minus theta lies in the second quadrant where tan is negative. So eventually you get tan theta. That means what? Whatever is the graph of tan in the open interval minus pi by 2 to pi by 2, exact same is the graph of tan in the interval minus 3 pi by 2 to minus pi by 2. Exact same will be the graph in the interval minus 5 pi by 2 to minus 3 pi by 2, and so on. And bingo, that's how you get the graph of the tan function completely. Right? So let's observe one thing, okay? Let's observe one thing which is extremely crucial in here. If you just focus on the graph of tan in the open interval minus pi by 2 to pi by 2, which is an interval of length pi. Do you agree? The interval minus pi by 2 to pi by 2 is the interval of length pi. Then exact same replica photocopy is the graph of tan in the next interval of length pi, which is open pi by 2 to open 3 pi by 2. Also in 3 pi by 2 to 5 pi by 2, 5 pi by 2 to 7 pi by 2, minus 3 pi by 2 to minus pi by 2, minus 5 pi by 2 to minus 3 pi by 2, and so on. That means what's happening? Even tan is turning out to be a periodic function. Why? Because it is repeating its behavior, or it is reoccurring at regular intervals. In fact, to be very precise, it is a periodic function with period pi. Why? Because whatever is the graph of tan, or whatever is the behavior of tan in this interval of length pi, exact same is the behavior of tan in the consecutive intervals of length pi to the right of this interval or to the left of this interval. Okay, so we have arrived at a fantastic conclusion about the tan function, that its period is pi. That's why it is sufficient for you to plot the graph of tan in just one interval of length pi and extract out as much information as you want from it, because in the consecutive intervals of length pi, the behavior gets repeated. Yes, also if you look at the graph as it is moving from bottom to top, it is sweeping all the real numbers along the y-axis from minus infinity to infinity. Do you agree? That means the range of this function is set of all reals. Domain, I already told you, range is set of all reals. So domain is restricted. Domain is all reals except every odd integral multiple of pi by 2, but range is complete real line. Yes, further, let's observe one more very, very interesting thing about tan, which is common sense as well. But yeah, just check out the points at which the graph is intersecting the x-axis. 0, pi, then 2 pi, 3 pi, 4 pi, and so on, minus pi, minus 2 pi, minus 3 pi, and so on. That means tan is 0 at every integral multiple of pi. But isn't that even common sense? How? Well, tan is sine upon cos. I know whenever sine is 0, cos is non-zero. For an angle, if sine is 0, for the same angle, cos is non-zero. That means sine upon cos is 0 when sine is 0. That means tan is 0 when sine is 0. And sine is 0 only at integral multiples of pi, and hence tan is 0 at every integral multiple of pi. Got it? And hence the set of observations about tan. This is its domain. Range is all real line. Tan is 0 wherever sine is 0. That means at every integral multiple of pi. Its period is pi. And I know as a matter of fact that tan pulls out the minus sign. Tan of minus theta is minus tan theta. Understood? Let's now move on to the next trigonometric function. Next up, we have the cosec function, which you know as a matter of fact is the reciprocal of sine. Isn't it? Cosec is 1 upon sine. Obviously, 1 upon 0 is not defined. So 1 upon sine will exist as a real quantity only when sine is non-zero. Or I can say cosec exists as a real quantity if and only if sine is non-zero. We know as a matter of fact that sine of an angle is 0 only when that angle is an integral multiple of pi. So we get that cosec exists as a real quantity only for those angles which are not an integral multiple of pi. Or in other words, I can say cosec of an angle is not defined when the angle is an integral multiple of pi. So cosec of integral multiples of pi doesn't exist. That means you can find out cosec ratio of any angle except integral multiples of pi, and hence the domain of the cosecant function is all reals except integral multiples of pi. That is the reason why in the graph of the cosec function you see dotted lines corresponding to every integral multiple of pi. Got it? Right? Now let's start plotting the graph of the cosec function. But even before that, realize one more thing. Okay, we know cosec is 1 upon sine. So wherever sine will be 1, cosec will also be 1 because it is 1 upon 1. Wherever sine is minus 1, cosec will be minus 1 because in that case it will be 1 upon minus 1, which is minus 1. So let's see. At pi by 2, sine is 1. So at pi by 2, even cosec is 1. At 3 pi by 2, sine is minus 1. So at 3 pi by 2, even cosec is minus 1. At 5 pi by 2, sine is 1, so even cosec is 1, and so on. Similarly, at minus pi by 2, sine is minus 1, so even cosec is minus 1. At minus 3 pi by 2, sine is 1, so even cosec is 1, right? And so on. Now, in the interval 0 to pi, you know, this is the graph of the sine function. And hence, in the interval 0 to pi, its reciprocal cosec will have this graph. Yeah? Similarly, in the graph, in the interval pi to 2 pi, this is the graph of the sine function. Do you agree? And hence, in the interval pi to 2 pi, its reciprocal will have this graph, and so on. Similarly, in the interval minus pi to 0, this is the graph of sine, so its reciprocal will have this graph. In the interval minus 2 pi to minus pi, this is the graph of sine, so its reciprocal will have this graph. And that's how even this graphical representation justifies that sine and cosec are reciprocals of each other. Isn't that mind-blowing? Now, one thing which is very, very crucial to observe here is if you look at the graph of cosec in the interval 0 to 2 pi, obviously open 0 to open 2 pi, obviously, because 0 and 2 pi are not included. Then, whatever is the graph in this open interval 0 to 2 pi, exact same is the graph in the interval minus 2 pi to 0. In fact, every other consecutive interval of length 2 pi, the graph is going to be same. Yes, and that brings me to the conclusion that cosec is a periodic function with period 2 pi. That was common sense as well. Sine is a periodic function with period 2 pi, so obviously its reciprocal will also be a periodic function with the same period. Okay, but yeah, we've justified this as well. Got it? So the period of cosec function is same as the period of the sine function, equal to 2 pi. Moreover, one more thing you observe. If I draw the lines y equals 1 and y equals minus 1, then as you can see, the graph of cosec is either on the orange line or above the orange line, or it is on the purple line or below the purple line. That means, if you look at the graph of cosec, it is sweeping the real numbers along the y-axis which are greater than equal to 1 as well as less than equal to minus 1. That means range of this function is all real numbers greater than equal to 1, union all real numbers less than equal to minus 1. This is the range of the cosec function. Cosec of an angle is always greater than equal to 1 or less than equal to minus 1, but it is never ever strictly between minus 1 and 1. Yes, because you can see absolutely no portion of the graph lying in or corresponding to the open interval minus 1 comma 1 along the y-axis. Yes, that's why cosec of any angle is never ever less than 1 or greater than minus 1. Never. Got it? This takes me to the list of observations about the cosec function. Its domain as justified is all reals except integral multiples of pi, right? Range is this, period is 2 pi, and I know as a matter of fact that cosec of minus theta is minus cosec theta. Also, one very, very beautiful thing to observe from here is that when we were talking about sine, cos, and tan, we were checking out the points of intersection of these graphs with the x-axis because we wanted to know wherever these ratios are equal to 0 or what are the angles for which these ratios are equal to 0. But in here, I just justified that cosec of an angle is greater than equal to 1 or less than equal to minus 1. It is never ever less than 1 or greater than minus 1. That means there is absolutely no angle for which cosec is 0. Okay, sine, cos, tan, yes, they were 0 for their respective angles, but cosec is never equal to 0. Okay, let's move ahead and talk about the secant function. Okay, then we know that sec is nothing but reciprocal of cos, right? And 1 upon something is defined only when this something in the denominator is not equal to 0. That means what do we get? That sec is defined only when cos is non-zero. I know cos is 0 only when the angle is an odd integral multiple of pi by 2. So sec will exist as a real quantity only when the angle is not an odd integral multiple of pi by 2. Or in other words, I can say sec of an angle is not defined when the angle is an odd integral multiple of pi by 2. So sec of an angle exists for every real angle except odd integral multiples of pi by 2, and hence the domain of the sec function is all reals except odd integral multiples of pi by 2. Do you agree? And that's the reason why in the graph of the sec function you have these dotted lines corresponding to every odd integral multiple of pi by 2. Got it? Because there is no sec value existing corresponding to these angles. Right? Now, before I jump on to plotting the graph, let's realize one more thing, that because sec is 1 upon cos, wherever cos is 1, sec is 1 upon 1, which is 1. Wherever cos is minus 1, even sec is minus 1 because it is 1 upon minus 1, which is minus 1. So that means at 0, cos is 1. So at 0, even sec is going to be 1. At pi, cos is minus 1. So even sec is going to be minus 1. At 2 pi, cos is 1. So even sec is going to be 1. Similarly, at minus pi, cos is minus 1. So even sec is going to be minus 1, and so on. Now, realize that in the interval minus pi by 2 to pi by 2, this is the graph of the cos function. So its reciprocal will have this graph. It's just working like sine and cosec, exact same fashion. Similarly, in this interval, this is the graph of the cos function. So correspondingly, this is the graph of its reciprocal sec in this interval. Okay. Similarly, this is the graph of the cosec function in the interval 3 pi by 2 to 5 pi by 2. So this is how sec will behave in this interval. And similarly, this is the graph of the cosec function in the interval minus 3 pi by 2 to minus pi by 2. So correspondingly, this is the graph of the sec function, and so on. So again, from the graphical interpretation, you can see that yes, sec is the reciprocal of cos. That's how they are behaving even graphically, right? In fact, again, if you observe, whatever is the behavior of the sec function in any one interval of length 2 pi, exact same ditto photocopy is the behavior of the sec function in all the consecutive intervals of length 2 pi, which means that even sec is a periodic function with period 2 pi. And that was bound to happen, isn't it? Because cos and sec are reciprocal of each other, so they are bound to have the same period. And hence I get the period of the sec function is equal to 2 pi. Moreover, allow me to draw two lines over here. One is y equals 1, another is y equals minus 1. What do you see? The graph of the sec function is either on and above the orange line or on and below the purple line. That means sec function is sweeping the real numbers along the y-axis, which are greater than equal to 1 or less than equal to minus 1. So obviously the range of this particular function is all real numbers greater than equal to 1 union all real numbers less than equal to minus 1. Exact same as the range of the cosecant function. Right? So what do we observe? That sec of an angle is greater than equal to 1 or less than equal to minus 1. It is never ever less than 1 or greater than minus 1. Which again means that sec of no angle is equal to 0. Sec is never ever 0. Got it? And now it's time to wind up the sec function by just recollecting everything that we've observed till now. The domain is all reals except every odd integral multiple of pi by 2. Range is this, which again justifies that sec of an angle is always less than equal to minus 1 or greater than equal to 1. It is never, ever, ever strictly between minus 1 and 1. Got it? Period as justified is same as the period of cos, which is 2 pi, and sec of minus x is same as sec x, which is the behavior exactly same as the behavior of cos. Why? Because cos and sec both are reciprocal, so they both gulp in the minus sign, and hence you get sec of minus theta is same as sec theta. Okay. Now, we know that cot is cos upon sine. Yes. And I also know when cos is 0, sine is non-zero. So whenever cos is going to be 0, cos upon sine will be 0. Do you agree? That means cot is 0 only when cos is 0. Cos of an angle is 0 only when the angle is an odd integral multiple of pi by 2. That means at every odd integral multiple of pi by 2, cot will be 0. That means at pi by 2, cot is 0. At 3 pi by 2, cot is 0. 5 pi by 2, 7 pi by 2, 9 pi by 2, and so on, cot is 0. Minus pi by 2, cot is 0. Minus 3 pi by 2, cot is 0. Minus 5 pi by 2, minus 7 pi by 2, and so on, cot is 0 at every odd integral multiple of pi by 2, because at these points, cos is 0. Now, let's move on to plotting the graph, okay? Just recall what was the graph of tan in the interval 0 to pi by 2. This was the graph somehow. So its reciprocal cot will have this graph. Yes? Similarly, in the interval minus pi by 2 to 0, this was the graph of tan. So its reciprocal cot will have this graph. In the interval minus pi to minus pi by 2, this was somewhat the graph of tan. So its reciprocal will have this graph. And similarly, in the interval pi by 2 to pi, this was somewhat the graph of tan, so its reciprocal will have this graph. Okay, when you keep on doing this, you get this to be the graph of the cot function. Yes? Now, what all do you observe? See, one very important thing is that whatever is the graph of cot in this interval of length pi, which is an open interval 0 to pi, obviously open at 0, open at pi, exact same graph, ditto copy, is in the immediate next interval of length pi, which is pi to 2 pi. Same will be the graph in the immediate next interval of pi, length pi, which is 2 pi to 3 pi, then 3 pi to 4 pi, 4 pi to 5 pi, and so on. Also, exact same is the graph in this interval minus pi to 0, which is also an interval of length pi. Exact same will be the graph in the immediate previous interval of length pi, minus 2 pi to minus pi, and hence similarly in minus 3 pi to minus 2 pi, and so on. Basically, whatever is the graph of cot in one interval of length pi, exact same is the graph of cot in the consecutive intervals of length pi. That means this particular function is periodic with period pi. Yes, and again, that's obvious. Why? Because cot is reciprocal of tan. Yes, whatever will be the period of tan, same will be the period of cot. It's justified right now also. Tan had period pi, so cot also is coming out to be a periodic function with period pi. What about the range of this function? Take a look at the graph as it is moving from bottom to top. Obviously, it is sweeping all the real numbers along the y-axis from minus infinity to infinity. So the range is the set of all reals. Got it? And hence, we have observed that the domain is set of all reals except integral multiples of pi, but the range is set of all reals. So domain is restricted, but the range is complete real line. Also, cot is 0 wherever cos is 0. That is at every odd integral multiple of pi by 2. Okay? Also, the period of cot is same as the period of tan, which is pi. And I know cot of minus theta is minus cot theta. Cot pulls out the minus sign. Yeah, this completes my discussion about the graphical representation of all the 6 trigonometric functions: sine, cos, tan, cosec, sec, and cot. Got it? Now it's time to check out some transformations of graphs. The first one is called the vertical stretch. What does it say? Let me tell you. It says how to plot the graph of k times f of x from the graph of f of x where k is some strictly positive real number. Two cases obviously arise in here. One when k is greater than 1, other when k is strictly between 0 and 1. Obviously, we are not interested in k being equal to 1, because in that case, both these functions are exactly same, so they both have the same graph. Let's begin with case 1, which says how to plot the graph of k times f of x from the graph of f of x if k is strictly greater than 1. We'll understand this from an example. Suppose I have the graph of f of x equal to sine x with me, and I want the graph of 2 times f of x, which is 2 times sine x. Yes, in here I'm taking my k to be equal to 2, which obviously is greater than 1. Let me use the conventional method to draw this graph. If I take x as 0, 2 sine x comes out to be 2 into sine 0, which is 2 into 0, which is 0. So I get 0, 0 as the point. Next, if I take x as pi by 2, 2 sine x becomes 2 sine pi by 2. Sine pi by 2 is 1, so I get 2 into 1, that is 2, giving me the point pi by 2, 2. Next, I take x as pi. So 2 sine x becomes 2 sine pi. That means 2 into 0, which is 0. Next, I take x as 3 pi by 2. So 2 sine x becomes 2 sine 3 pi by 2. Sine 3 pi by 2 is minus 1. So you get 2 into minus 1, which is minus 2. Lastly, if I take x as 2 pi, I get 2 sine x as 2 sine 2 pi, which is 2 into 0, which is 0. When I join these points, this is the graph of 2 sine x that I get. Got it? So this was the graph of f, and this is coming out to be the graph of 2 times f. What do you observe? Can you see that the graph of 2 times sine x is kind of an elongated version of the graph of sine x? It's like somebody has stretched the graph of sine x. Yes, in fact, let me tell you something. See, this point is 0, 0. This point is pi by 2, 1, and this point is pi by 2, 2. Yes, this is pi, 0. Here, this is 3 pi by 2, minus 1, and this one is 3 pi by 2, minus 2. And lastly, this is 2 pi, 0. What do you observe? That if x, y is a point lying on the graph of sine x, then correspondingly x, 2y is the point lying on the graph of 2 sine x. That means, to be precise, if I stretch the graph of sine x twice along the y-axis, I will get the graph of 2 sine x. Bingo. In fact, this is not just true for the sine function. If you have the graph of any function f of x with you, and you stretch that graph vertically along the y-axis k times, you will end up getting the graph of k times f of x, where k is greater than 1. Now let's talk about case 2, which says how to plot the graph of k times f of x from the graph of f of x if k is a real number strictly between 0 and 1. For that, let's check out this example. So I have the graph of f of x equal to sine x with me, and I want to plot the graph of half times f of x, which is equal to half times sine x. So in here, obviously, I'm taking k to be equal to half, which is definitely strictly sandwiched between 0 and 1. Again, let's use the conventional method to do so. If I take x as 0, half sine x comes out to be half into sine 0, which is half into 0, which is 0. Next, if I take x as pi by 2, half sine x comes out to be half sine pi by 2. That means half into 1, which is half. Next, if I take x as pi, I get half into sine pi, which is half into 0, which is 0. Next, if I take x as 3 pi by 2, half sine x becomes half into sine 3 pi by 2. That means half into minus 1, which is minus half. And lastly, if I take x as 2 pi, half sine x becomes half sine 2 pi, which is half into 0, which is 0. When I plot these points, this comes out to be the graph of half times f of x, that is half times sine x. So in here, in the same Cartesian plane, you have two graphs. One is the green graph, which is the sine graph. Other is the pink graph, which is half times sine graph. What do you observe? Can you see this half times sine x is kind of a compressed version of the graph of sine x? It's like somebody has shrunken the graph of sine x to give you the graph of half sine x. Yes, in fact, to be precise, carefully observe, this is 0, 0. This is, or let me say, this point is pi by 2, 1. This point is pi by 2, half. This point is pi, 0. This point here is 3 pi by 2, minus 1. And this one is 3 pi by 2, minus half. And this one is 2 pi, 0. What am I wanting to deliver from marking these coordinates, which are lying on both the graphs? I'm just trying to make a point here that if x, y belongs to the graph of sine x, then x, 1 by 2 times y, that means x, half times y will belong to the graph of half times sine x. That means, to be precise, if you shrink the graph of sine half times along the y-axis, you will get the graph of half sine x. That's it. The good news is that this not just works for the sine function, but in fact, it works for any function f. If you have the graph of f with you and you shrink it along the y-axis a times, you end up getting the graph of a times f of x, where a is a fraction strictly between 0 and 1. And hence, now we know that if a is a number strictly greater than 1, then don't do anything. Just take the graph of f and stretch it along the y-axis a times. You will get the graph of a times f of x. And if a is a fraction between 0 and 1, then don't do anything. Just take the graph of f and shrink it along the y-axis a times. You will get the graph of a times f. That is all about the transformation, which is vertical stretch. Now we have to talk about another transformation, which is called horizontal stretch. What does this entail? Let me explain this to you. The question is how to plot the graph of f of ax from the graph of f of x, where a is some positive real number. Again, two cases arise. One, when a is greater than 1. Other, when a is a fraction strictly between 0 and 1. Let's begin with case 1. That is how to plot the graph of f of ax from the graph of f of x, where a is a number strictly greater than 1. We'll understand the answer of this question from an example. So in here, I have the graph of f of x equal to sine x with me. I am interested in plotting the graph of f of 2x, which is sine of 2x. So in here, my a is equal to 2, which is greater than 1. Let's use the conventional method to plot this graph. If I take x as 0, sine 2x becomes sine of 2 into 0, which is sine 0, which is 0. So I get the point 0, 0. Next, if I take x as pi by 4, sine 2x becomes sine of 2 into pi by 4, which is sine pi by 2, which is 1, right? So I get pi by 4, 1. Next, if I take x as pi by 2, sine 2x becomes sine of 2 into pi by 2, which is sine pi, which is equal to 0. So I end up getting pi by 2, 0. Next, I take x as 3 pi by 4, so sine 2x becomes sine of 2 into 3 pi by 4, which is sine 3 pi by 2, which is minus 1. And hence, this point becomes 3 pi by 4, minus 1. Lastly, when I take x as pi, sine 2x becomes sine 2 pi, which is 0. And hence, I get pi, 0. When I join these points, I get this to be the graph of sine 2x in the interval 0 to pi. Okay. Now, tell me one thing. If x lies here between 0 to pi, then obviously pi plus x lies between pi and 2 pi. Yes, I am interested in sine 2x. That means sine of twice of pi plus x, which is sine of 2 pi plus 2x. Now, sine of 2 pi plus anything is sine of that thing. So this is sine 2x. That means what? That means what? Whatever is the graph of sine 2x in the interval 0 to pi, exact same is the graph of sine 2x in the interval, which is pi to 2 pi. Do you agree? Yes. And now it's time for you to do some real observation. See, you have two graphs in here in the Cartesian plane. The green one is sine x and the pink one is sine 2x. If you carefully look at these coordinates that I have marked, deliberately, you will see that in here at pi by 4, sine 2x is becoming 1, whereas sine x becomes 1 at pi by 2. Yes, then sine becomes 0 at pi, but sine 2x is becoming 0 much before pi at pi by 2 only. Next, we know that at 3 pi by 2, sine is minus 1, but sine x is becoming minus 1 much before 3 pi by 2 at 3 pi by 4 only. And so on. This basically results in what? See, the green graph, if you see, that is the graph of sine, it is completing one cycle in the interval 0 to 2 pi. Yes, one complete cycle it is, completing in 0 to 2 pi interval. Whereas, if you look at the pink graph, it is completing one cycle in the interval 0 to pi only. In fact, in 0 to 2 pi, it is able to complete 2 entire cycles. Yes, so sine is completing one cycle in 0 to 2 pi, whereas sine 2x is completing 2 entire cycles in 0 to 2 pi. This simply means that if you take the graph of sine and you shrink it horizontally 2 times, you will get the graph of sine 2x. That's it. That's the observation from here. In fact, to convince you more on this, let me show you the simulation. Okay, let's check this out. Right now, the graph that you can see is the graph of sine ax, where a is equal to 1. That means this is the graph of sine x. You can clearly see in the interval 0 to 2 pi, it is able to complete one entire cycle, right? Now let me replace a with 2. This is the graph of sine 2x. You can clearly see that in the interval 0 to 2 pi, this graph is completing two entire cycles. Yes, now I'm replacing a with 3. This is the graph of sine 3x. And what's happening here? In the interval 0 to 2 pi, carefully observe, it is able to complete 3 cycles. This simply takes me to the conclusion that if you have the graph of sine x with you and you shrink it horizontally along the x-axis by a times, you end up getting the graph of sine ax, where a is a number strictly greater than 1. In fact, this is not just confined to sine x, this is valid for every function f. If you have the graph of f of x with you and you shrink it horizontally along the x-axis a times, you end up getting the graph of a times f of x, where a is strictly greater than 1. Got it? Next, it's time to address case 2. Okay? That means, what is the graph of, or how to plot the graph of f of ax from the graph of f of x if a is a fraction strictly between 0 and 1? Again, let's understand this from this example. So in here, I have the graph of sine x with me. Let me take this as f of x. Okay, and I want the graph of f of half of x, which is sine of x by 2. Okay, in here, deliberately, I have drawn the graph of sine x in the interval 0 to 4 pi. Let's, in the same interval 0 to 4 pi, plot the graph of sine x by 2. Let's begin. If x is 0, sine x by 2 gives me sine 0, which is again 0. If x is pi, sine x by 2 gives me sine pi by 2, which is 1. If x is 2 pi, sine x by 2 gives me sine pi, which is 0. If x is 3 pi, then sine x by 2 gives me sine 3 pi by 2, which is minus 1. And if x is 4 pi, sine 4 pi by 2 becomes sine 2 pi, which is equal to 0. When I join these points, this is the graph of sine x by 2 that I get. So now you have both the graphs with you in the same Cartesian plane. The green one is sine x, the pink one is sine x by 2. What can you observe? See, it's very simple. If you just focus on 0 to 2 pi interval, the green graph is able to complete one cycle, whereas in the same interval 0 to 2 pi, the pink graph has only completed half cycle. If I talk about the interval 0 to 4 pi, the green graph is able to complete 2 cycles, whereas the pink graph has only completed one cycle in 0 to 4 pi. That simply gives you the answer. If you take the graph of sine x and you expand it, stretch it horizontally along the x-axis half times, just half times, you will end up getting the graph of sine x by 2. Yes, that's it. In fact, if you would have had sine x by 3 as the function, the answer is of the same fashion. If you have the graph of sine x with you, just stretch it, expand it along the x-axis 1 by 3 times. You are going to end up getting the graph of sine x by 3. Okay, and this observation is not just confined for sine function, it is actually relevant for every function f. If you have the graph of f with you, you just need to stretch it horizontally along the x-axis by a times. You will end up getting the graph of f of ax, where a is specifically a fraction between 0 and 1. Okay, and that ends my discussion over the transformation horizontal stretch. And we have obtained the answer, what? That if a is strictly greater than 1, then you take the graph of f of x with you and you shrink it along the x-axis by a times, you will get the graph of f of ax. And if a is a fraction strictly between 0 and 1, then take the graph of f and stretch it horizontally along the y-axis a times, you will end up getting the graph of f of ax. Okay? To sum it up, let's quickly recall that if x represents the input for a function f, then f of x represents the corresponding output. So I can say that the vertical stretch transformation occurs when a positive constant a is multiplied by the output. Yes, specifically when a is greater than 1, the graph of f stretches vertically. And when a is strictly between 0 and 1, the graph of f shrinks vertically. Yes, similarly, the horizontal stretch transformation occurs into picture when positive constant a is multiplied with the input of the function. To be precise, if a is greater than 1, the graph of f shrinks horizontally, and when a is between 0 and 1, the graph of f stretches horizontally along the x-axis. Of course, there are many more transformations to study. Till now, we are only able to get through with two of them, the vertical stretch and the horizontal stretch transformations. And also, I have already talked about the vertical flip transformation as well. So, in total, three transformations we've covered. We'll talk about the remaining ones in the next session. I'll meet you then very, very soon. Till then, you take care and keep learning. Thank you.